before I ask for questions, I just want to make sure everybody's aware of this, that I have classes for my office hours. Normally, right after class, I'm up in my office for an hour, so that's for sure. So it'd be from 2 to 3. Then on Tuesdays and Thursday, I'm in my office from 11 till 12. Like, I try to guarantee that time slot. I got a lot of other stuff. I've got meetings and all these things that are scattered, so I can't predict exactly when I'm available. But if you have problems, send me an email. Worst case scenario, I can do a Zoom meeting with you. I mean, if I'm at home and stuff like that. I'll try to help you anywhere I can. But just like everybody else, I'm scattered throughout the day where I have to be and what I have to do. So that's the first thing. Second thing, questions about the homework, or really anything related up to the point of today's lecture. You all got the homework, right? Any questions at all? Yeah.
Did you work number 43?
Yeah. Okay. All right, so for 43, this is sort of a kind of typical problem. I'd like to do one that's a little more complicated with like a current lasting after t goes to infinity, something where you're going to have to, more things happen, but we'll do this one. So this is 443, and it's 24 volts, 2 ohms. And you got a switch. And below here you have 12 volts, 2 ohms. I'll show you a trick with this one too. And 2 ohms. Then you have 1 ohm. The switch opens at t equals 0. Okay. Then, what is this? Resistor 1 ohm. And an inductor of 2 henries. And then a resistor of 4 ohms. And they want this. Don't worry about the voltage. Only thing you care about when the inductor's in the circuit for these transient problems is the current in the inductor. Y'all hear in class? It's exactly this identical in terms of the process and the idea to the voltage in a capacitor. Everything else you want depends on the voltage in the capacitor or the inductor's current, the current in the inductor. Y'all hear me, class? So we're going to start, when we talk, first we're going to talk about this. Now, with the inductors, and I'll try to put it here, when you have an inductor, the first thing you want really is the current through the inductor at t less than or equal to 0. That's where the transition occurs. I think I put this on the board last time. I'm not sure if these steps are outlined clearly in the book or not, but this is the way you do it. Second thing you take a look at is the current in the inductor as t goes to infinity. Identical to the capacitor's voltage if you look at the steps. You all follow me, class? Can you all see it in the back, guys? Third thing, you find R Thevenin. Now that's the Thevenin equivalent resistance that you would measure across the terminals if the inductor's taken out. Am I clear on that, everyone? It's exactly like the capacitors are though. And I might as well just do it here. The time constant for an inductor in a resistor is going to be L over R Thevenin. You all follow me? Unlike the capacitor, which is R times C. Now, if you're just cramming a lot of times on Thursday night, or whenever you have it, what you'll find is you'll mess that up. You'll put L times R Thevenin, because the time constant before was R times C. Don't cram. Spend time, preferably daily, but at least every other day. Do the homework in between classes. It will keep you safe. Trust me on this one. Spend time. Finally, the fourth thing is you put the thing together. You say IL is a function of t. We only care for t greater than 0, less than 0. That value is not of interest usually. I might ask for it. Obviously, you need it, right? But it's going to be equal to some constant, and I can call it K1 plus K2 e to the minus t over tau. I want to just spend a moment and ask you a question. Remember, this is the current through the inductor. What is the K1 that, can you all see it in the back, by the way? The K1, what does that represent in your own words? The current at t equal infinity, right? Now K2, you don't know for sure. You may have to solve for that. If there's a current at infinity and a current just as a switch transitions from 0 minus to 0 plus, you're going to have to solve for this value. You all hear me, class? So you can't always assume it's the current for t less than 0. That is a common mistake. We clear on that? How many understand this? Now let's do the problem. When you look at this, I can show you a few tricks with this one. And they're not really tricks, they're just things to keep in your pocket. If you look at this, for t less than 0, that switch has been on forever, correct? I'm going to show you a trick. So I can go ahead and I can say, I can take that 2 ohm and put it straight down. Do you agree with that? I can do it. I don't have to do it that way, but I can. So I can say, this is really 2 ohms and 24 volts. This would be for t less than 0. And this is plus to minus 24. Then you got this, forget the switch. I have 12 volts here. And I'm going to rearrange this. I'm going to put the 2 ohm up top. It'll be a little easier to see, I think. It won't matter, they're in series. And then finally, now over here, what does the inductor look like? What do you represent it as for t less than 0 and y? Anyone? A what? I think I heard it right. Say it again, whoever said it. Short circuit. All right, you got to speak up, right? Did y'all hear that, class? That's all it is. If there's nothing changing with time, and it isn't, because for t less than 0, you can assume it's been on forever before that time, since the beginning of time. So you can just put a short circuit there, and that's the current I want. But I have 1 ohm and 4 ohm. Can you all see that's 5 ohms? How many see that? Just represent as 5 ohms. And I didn't put this, but I'm going to assume this is the direction of current IL of t that I'm after. So really, I can just say that what I have here really is 5 ohms here, and I'm after this current now. This would be IL for t less than 0. I have to make sure everybody sees that. Do y'all see what I've done here? How many do? Now, how are you going to solve that? Well, you can do it a lot of ways. You also could do 2 loops. How many see that? Yes, sir.
How can you combine the resistors if there's a short circuit in between?
Class, anybody want to answer that? Will it matter if you just want the current 2 series resistances, any order they're in? Would it matter? What's always between the 2 resistors? Wire. Correct, class? It doesn't matter if you put one in front of the other. The combination is the same. That short circuit has nothing at all to do with the resistance values. It's a wire. I hope I answered your question. Sometimes students can answer it better than professors. I found that out. Grad students are the best. Yes?
For the 2 ohm resistor, doesn't matter that you put it in front of the 12
12 voltage?
You're talking about this, right?
Yeah.
Now, hear me on this. The only thing I care about is the current here, right? Is there any physical difference in the outcome over here if I take the 12 volts, put it there, and the 2 ohm here?
Yes, no.
How many see there isn't? There won't be, right? Because there is nothing in parallel series. Now, I want to say this. You can't do that if there's complexity, like if there's a resistor here and then another resistor here. You can't do that. But here, it's 2 series components. As long as the plus stays on top, I don't care if I slide this, and I always think of that, slide this down here and slide this up here. It has the same effect. Make sure you see that. We good with that, class? Over here, you all with me? Okay? Now, I'm going to tell you, I'm going to show you a trick. Yes, you're right. We can ground this, and we can find V1 there, or just V, and then we can solve that with nodal or mesh. How many see that? I'm going to show you a trick. Remember I showed you the Thevenin to Norton conversion for current source in series with the voltage turned into, voltage source in series with resistor turns into a current source in parallel with resistor. How many remember that? Good. That's the guy you want to go to. These are tricks you're going to find very useful solving this type of problems and problems to come. So to show that, what I'm going to first do is say, I'll do it right here. I'll try to make sure you can see it. I want to take some time. Now, I'm not going to go ahead and prove this right now, but what you can do is this. If you have a voltage source, regardless of the value, I'm putting a battery here, in series with the current, or with the resistor, R, I'll just call it R. Sometimes they call it R Thevenin, but it doesn't matter. And you have 2 dangling terminals, plus to minus. You all see that? What that is identical to is finding the short circuit current here. Short circuit current would be, if you just did that. What is the short circuit current there? By looking in terms of the voltage and resistance. Class? Just the voltage divided by the resistance. Do you all agree? That's what short circuit current means. Well, what it means is, I can say that this is exactly identical to this, and then you'll see, I think you'll see why. You can put I short circuit here as simply the V, and I call it, you can call it V open circuit if you want, divided by R Thevenin, and then you put, and I'll get out of the way, R Thevenin in parallel with it, and here's the 2 dangling terminals. You can call that A and B if you want, A and B. Now those 2 circuits are electrically identical in terms of what will happen to the output once you place those, replace one with the other. The effect on the overall circuit. How many see that? How many remember it now? You guys do? In the back, no? This is a powerful technique. It's a very nice thing to know. It's like Thevenin's analysis because it makes everything so much easier. Now look over here. See, I have a voltage source in series with the resistor. You all with me? How many see that? Just look right here. I can replace that. Boy, I'm running out of board. I can replace that, with a current source going up. All right, and that current would be 24 by 2. So this current right here, call it I1, would be 24 by 2 amps. Then you take that 2 ohm resistor and put it in parallel. You with me? How many see this? Do you not see it, guys? I mean, I'm not seeing all these. Do you see it in the middle or no? You understand? You don't see it in this? Well, how can I help you? To ask the question. Yeah.
No, I was just like, I couldn't see.
Because I was in the way. All right, now, can you all understand what I'm doing, class? I'm showing you a simple technique for taking this in series with that in series, voltage source in series with resistor and turning it into a current source here, sorry, I'm in your way, just that voltage by the resistance and putting that resistance in parallel. You all with me? Now, I'm right here. You'll notice I have another voltage source in series with a resistor. Can everybody see that? So I'm going to do the same thing, and I have to have the same sense of current. I'm sorry, I'm going to have to put this 2 Henrys here. So what I'm going to do over here, and remember, these are effectively A and B. That's A, that's B, and you'll notice they're in parallel. Can you all see that? So I can take that second one and just say, well, it's another current source here. This current is going to be, and I'm going to put it down 12 over 2 amps. So this current, call it I2, is 12 over 2 amps. I'm showing you the trick. This is an easy way to do this problem. That's what I'm trying to tell you. Now, I'm here. That's the current I want, right? Can you all see that? Far back, can you guys see that? And I'll get out of your way from here. You with me, class? Now, I can just put that in here. I got to put the 2 ohm next to this too. For that. Remember, that's 2 ohms as well. There's 2 ohms here, 2 ohms there. They're in parallel now, but the current sources are the electrical forcing function. Now you put the 5 ohms. I'm going to ask you how to do it. I bet you most of you see this. Now I just put the 5 ohms here. And this is the current I want right here for ILT less than 0. Take a moment. Do you all see what I'm doing? I have to make sure you see it. This is an easy, it simplifies this, makes it trivial. How many see this? Can you all see it or not? I'm worried. Can you see what I wrote or not? If you can see it, do you understand it? How many understand this? This is critical. Now, if you don't understand it, see me or let me know. Let me try to help. That's what I'm paid to do. Now, what do you see can happen here? How about if I make 24 by 2? Is that 12 amps, class? I'm going to simplify that. I got 12 amps. What about this? 12 by 2 is 6 amps. Just making sure you can read my writing. Sometimes I can't. All right, now, we're not done yet. What else might you simplify? Take a look. How about 2 and 2 is 1 in parallel? You agree with that? Down here, guys? I'm not trying to insult you. I'm just making sure. Maybe you can't read my writing, which is understandable. So this is really just 1 ohm, isn't it? It doesn't matter where they are, they're in parallel. What? Right? How many see that? Anything else we can do? There's 2 things that can be combined that are pretty obvious. The current sources. I got 12 amps. Then it's being pulled from the bottom rail, put up here. You all see that? Then I got 6 amps. Pulled from the, can I combine them into 18 amps? How many see that? Yeah, make life easy. Do you all see that back there? Now, if you don't like this, well, you don't have to do that. You can write loop equations or nodal, I don't care. But this is easy. Make life, look, your life is hard enough. Make it easy. So I'm going to get rid of this and make this 18 amps. You'll be able to go through this fairly rapidly when you get used to it. But it trivializes these problems, makes them laughable. Really. I mean, mechanical engineers, industrial, civil, whatever you are, I'm sure you see things in your major that make problems that could be a little difficult trivial once you start working a lot of them. Right? That's the same way here. Now, look at this. How do I get this current? I have 2 resistors in. I would use current division if I knew the current going through them. Do I? Yes. So what is this current that I'm after here? Class? It's 18, right? Times the opposite resistance over the sum. Or, what is it?
3 amps.
Can you all see that, class? Give me a show of hands if you can see it. I'm not trying to make light of this. I'm really trying to underscore, it's not that hard. I mean, you don't have to do it this way. But for me personally, I try to go the obvious, easy route. There's so many ways to mess up. Minimize the number of ways you can mess up. So we have that current, which would be this current, right? What is it? 3 amps. How many agree with that? Far back. All right. Hard to get a read on everybody. With me? Next. I'm going to erase this. I need this. What time is our game, by the way? What time?
3:30.
Okay. Don't. Back in my mind, I'm thinking everything I need to do before this place gets locked down in the morning. All right. So now I have that. Now the switch opens. If you don't mind, I'm just going to erase this entire lake here. Does everybody understand why? If you do, raise your hands. Once that switch opens, it effectively takes this entire thing out. It says, if it doesn't exist. Do you agree with that, class? I'm going to say this right. Far back. Yeah, he's doing something else. Okay. Now, this is the circuit that's remaining. What was this? 1 or 2? 1? Okay. Is that right, class?
Yeah.
All right, now we're going to go for the current as t equal to infinity. What does the inductor look like as t goes to infinity if there's nothing time varied? Class? I can't hear you. What is it? It's replace it with a short circuit. You all with me? I mean, there's no wrong answer here. If you want to say a wire, it's fine. Whatever, something that really lets me know you might as well just put a wire across it. So it looks like this. Right? And that's the current. Now I want this current. This would be I as t goes to infinity. What is that current? Just by looking. People? Well, I got 24 volts. And I got, let's see here, 7 ohms? 24 by 7. Do you all agree with that? It really is that easy. So I'm going to leave this as 24 by 7. Now I hope that's 1 ohm is right. I think it's better. Anymore, I don't trust myself. You with me, class? Everybody okay with that? What's the next thing? What? What? R7, thanks. Sometimes I think I'm going deaf. All right, so what is R7 going to be? Now this is important. I just happen to put a wire here, but if I open that, I'm trying to show you the image. Just rip it out, right? Those two terminals indicate where you want the Thevenin equivalent resistance. Does everybody follow me? But there's a source left, right? It's a voltage source. What do we do with a voltage source?
Short circuit.
Wire short circuit, they're all correct. So I make it this. All right? What's the Thevenin, this one you better get. What's the Thevenin equivalent resistance between those 2 points? 7 ohms. Do you all agree with that? Show of hands if you do. All right, at least I'm getting something. So now I got R Thevenin is 7. What was L? Was that 2 henries?
Yeah.
All right, so this is going to be 2 over 7. The units would be seconds. I'm just going to leave it as 2 over 7. I don't really care about the value at this point. Are you with me? What's the next step? Now this is important. Now I go to this thing, right? Now you're right about that, whoever said that. We know what K1 is, which is the current as t goes to infinity, which is this one. So now I come over here, I'm going to write the equation that we're going to we're going to go down and just get all the values to make sure everybody sees it. So I know that IL is a function of t, and this would be for t greater than or equal to 0 is equal to some K1 plus, I call it K2, e to the minus t over tau. We have tau. Do you agree with that? Make sure you see it. Now I replace K1 with the value of the current as t goes to infinity. You understand the reason for it? And that's, what is it, 24 over 7. So now I say this is 24 over 7 plus, I still have K2 e to the minus t over tau, right? But how do I figure out what K2 is, somebody? Evaluate that equation at t equals to 0, right? So at t equals 0, e to the minus 0 is 1, right? So I have K2 here. Now, what is the current at t equals 0? It is the same current as t equals 0 minus or 0 plus. It's this current. You agree? So you put 3. And now, you can find K2, right? If you want, what would it be? Well, it doesn't, I mean, I don't care how you do this. It's going to be 3 minus 24 over 7 would be K2. Let me leave it like this so everybody knows where I got everything. Y'all with that, class? Amanda, did you ask that? Who asked this? All right, is everybody good with that? All right, now, yes, sir.
I thought K2 would just be the current as
That's K2. You can't read my writing. This is K2, this is K1.
I thought K2 would just be the current as t.
No. Current, here's the deal. Now, this is a very important point. When the switch transitions from t less than 0 to t greater than, that current doesn't instantaneously change. It can't, because it would imply an infinite voltage. The current before is the current after. So after the switch closes, and now we're using this equation, we get K1 by looking at infinity. Got me? That's the current at infinity, but to get K2, we have to put the current here at t equals 0. That's the current less than t equals 0, which is the current just as the switch transitions. You with me on that one? So you put that here, so that would be K2. Do you agree with that? Everybody with me? Now that's the current. What did they ask for though? Didn't they ask for a voltage through a resistor? I think. They had this guy. Now remember, we know this. Please watch this. I now know for t greater than 0, I know my IL of t. I know that for all time. Correct, class? Please watch this. Are you with me? What's that current? What's the voltage going to be across this resistor? You all see all that current flows in that resistor, right? What's the voltage going to be? Volt. It's just going to be that resistance 4 times the current. Do you all see this, class? So it's going to be 4 times this. And if you want, you can put K1 as K1 is, what is it, 24 over 7, and K2, we calculated right here, and then you can do the multiplying. Now, I gave you the answer and solution. Is that what he has, basically? He's going to, he might put the actual values, like decimal values, I don't know what. That, in essence, is the way he solved it. You all with me, class? Somebody tried that problem. Listen, I really appreciate if you don't get behind, because you're going to get hammered coming up, because it gets much more complicated very quickly. And I mean that too. Like in the next week and a half, it goes from, this is fairly easy, basic physics. It's going to get complicated, so I'm trying to get everybody up to speed. Because then you can have this tremendous confusion where I don't know what you're doing. And that's where you can really get hurt. So, best I'm encouraging you. You with me, class? These are transient problems. You had these in physics, right? The basic transient phenomenology, you did, trust me. If you had physics, if you had it here at least, you had that. How many remember at least vaguely these kind of problems in physics? Now, there's honest students here. If you don't remember them, I don't know, man. I mean, I've heard all sorts of horror stories from people transferring in, and I don't know what to tell you guys, but this is supposedly basic stuff. There's nothing really outlandish here. All right, you all with me? You got another one for me, or can I move on? Anybody? Anybody? Now, at this point, I'm gonna tell you this, because I get these questions routinely. What's on the quiz? You're responsible for both RC circuits and RL. Now, if you're good guessers, you probably guess an RL circuit because you haven't seen one. And you probably are right. Have I made it out? No. You with me? In other words, do all the homework. Don't do one. Oh, that's the problem. No. Do it all. Make sure you understand it soundly. And please don't get behind right here, because we're about to jump into another topic in the next chapter. Now, any other questions about these? That was a great problem, by the way. It had everything I wanted. It had current that's not zero infinity, current initially that isn't zero, and enough complexity so you would either, if you wanted to, you could do nodal in that inner part, or you could do mesh, but the easy way is Thevenin Norton equivalent, in my opinion. Y'all with me, class? Find the easiest way and you know how to do it. And remember, Thevenin equivalent is the thing you gotta really rely on with a lot of these. Okay? Everybody with me? Okay, where we're going is the next chapter. Now this is stuff, if you pay attention and do what you're told, you're gonna fly through it. But if you get behind here, I mean, there's obviously some very intelligent people, but there are going to be people that are going to struggle and panic. That's as good as I can do. I'm not trying to threaten anything, I'm trying to encourage, but it's very hard sometimes with a game like Arkansas to get serious. And I hate to see people fail. And it happens all the time. All right, next. So this is the next chapter, and here it gets into something much more relative to what we deal with today. All right? And this is going to be constant frequency of excitation or excitation. How many know the wall outlet is not DC? Just show me. What frequency is it in? That's the voltage is 120 volts. What frequency? 60 hertz. How many know it's 60 hertz? You're kidding. You do, don't you? It's not Europe. It's not 50. Europe is 50. Do y'all know that? Anybody here in the military? You know what Europe is. If you ever go to Europe, you got to get an adapter. You got to make sure the 60 hertz, 120, is going to adapt to the 200 and whatever is 20 over there, 50 hertz thing, and you don't mess up your equipment, because people blow up stereo equipment all the time. I can tell you stories about this. Look, I do a lot of work in the military. Last thing I'm going to do is travel to any country and not know where the power grid is. I don't have a nice stereo anymore, but it wasn't because of that. Anyway, that'll happen. Okay, now, here's what we're talking about. The mathematical model for what happens at that terminal, voltage-wise, is this. You would have a symbol, but this isn't a constant value. It's going to be V of t. It is time varying. And that V of t in the time domain would have a value V0, that's the magnitude, and it would be cosine of omega t. I'm not going to put a phase angle in there. The units would be volts. Are you with me? Now, what does it look like is the next question. You've had physics. Sines and cosines are like second nature to most of you. If this is time, this waveform V of t that I've drawn there would look like this. It's called a periodic waveform that repeats itself. The peak magnitude here would be V naught, and it doesn't just start at zero, it goes on forever for all intents and purposes. Can everybody appreciate what I'm trying to draw here? With me? Now, that's in the time domain. This is time. This has a value of V naught. It will have a maximum negative excursion of minus V naught. You see that value of omega right there? That's a common term. Mechanical, I'm sure industrial, all the engineerings have it, so does physics and math. Omega is a frequency in radians per second. If you multiply that by time, radians per second times seconds is radians. Radians is a measure of angle, measurement of angle. You can also put it in degrees. Nevertheless, you have to make sure on the calculators, this is just a hint for later on, if you're doing a cosine in radians, make sure your calculator's in radians. Cosine degrees, make sure it's in degrees. How many have made a mistake like that at some point in your career? If you haven't, you really haven't done anything. Because I've made that more times than I can care to admit. But just remember that. Now, in terms, omega is units of radians per second. When we have a frequency, the symbol is F. F is in hertz or cycles per second. For instance, the wall outlet is 60 hertz. That means there are 60 periods or 60 full, I call them periods, that would occur in a second. Now, I'll get to that in a second. So whatever this is, that's in hertz or cycles per second. Omega is 2 pi f. How many know that? Omega, and this is, I mean, mechanical engineers, I'm sure industrial, civil, every flavor we have in here, I'm sure you've seen that in physics as well. Probably in your math courses, but I don't know that for a fact. So this is in radians per second. Now, I didn't add a phase angle there, I could. When I come back over to here, there's a couple things that are important to see based on this. The actual distance from here to here in the time domain is symbolized as t. It's called a period. You don't need to know that, but this is actually equal to 1 over f naught. You with me? If you have cycles per second and invert it, you get seconds per cycle. Y'all with me, class? How many remember that? At least I get an idea. It's good for me to see who's kind of with me on this thing. Now, all that's great and well, but so what? So why are you talking that way? Because we're going to do analysis in the frequency domain, but we're going to make it much, much, much easier than writing differential equations. Because you're going to find out you are not going to be fans of writing differential equations with that as the forcing function, or the solutions you go a little nuts on. At least most people do. So we do a couple of tricks. So first, we do this. How many know that there's something called Euler's identity that says e to the j omega t is actually equal to the cosine of omega t plus j times the sine of omega t. Omega t can represent as an angle. How many know that? Anybody remember the guy's name that law is given? Euler's, not spelled O-I, it's E-U. Euler's, yes sir.
What is that?
This is a J, and I'm about to get there, you're ahead of me. J is equal to the square root of -1 mathematically, which is just obvious, right? No. We're in a domain now that is non-observable. Anytime you see J, if anybody takes quantum mechanics, you're going to see this all over the place with the Schrodinger equation. Some of you think, oh, I'll never do that. You watch and see. Quantum engineering is coming down the pike, and a lot of you probably are going to end up doing something with it. You know about quantum computing? Anybody? You ever hear that term? Good, you can tell me how it works, because I know. But I'm going to level with you. You probably, if you haven't dealt with you deal with imaginary terms, don't you? In your math courses, and surely in engineering you have to use that all the time. We call it something else. We call it I over in math. Yeah, you did. You know why we don't call I in electrical and computer engineering? That's current. Yeah, we don't like to confuse ourselves more than necessary. We're confused enough. So we use the term J. That's the reason. So if you're coming from math and you say, well, we called it I. That's all the reason is for why we don't. You with me? Okay, don't worry about that. The only thing it means is this, and I'm not going to go too far afield here. If you said you wanted the real component of this, let me talk just, if you want the real of e to the j omega t, there's the expansion with Euler, it would just be cosine. That's the only thing you gotta remember at this point. You with me? You ignore the sign. Nevertheless, when we do analysis, what we found is this. If I know v of t here is equal to the real part right here of some v naught e to the j omega t. I'm going to take a stab here and make sure everybody follows me. Remember, RE just means real part. Ignore the j, basically. Anything that's a coefficient of j, ignore it. Now, if we do that, we can simplify life in a big way, and I'll show you how. Because if that is true, if I say I'm going to use V naught e to the j omega t as my driving voltage, everything else, all the voltages and currents will have a e to the j omega t associated with them. Just trust me on that, they will. When you do the differential equation, something wonderful happens. Every time you have a time derivative, you just get a j omega in front of it, and every time you have, or basically that's it. It's every time there's a time derivative, you get j omega. Then you can solve for these, what they're called phasor currents and voltages, and I'm going to show you how. And you can take those and very easily solve differential equations. And instead of having all these integral differential equations, you have algebraic equations that you can solve. Makes life easy. How many, and I'm not going to do that, how many remember Laplace transforms? What was the one beautiful thing about Laplace transforms if you're trying to solve diffie-cubes? Instead of figuring out integrating factors and God knows what else they taught you, you had an equation which is s squared plus some s plus some constant that you had to factor and then do a partial fraction expansion to get the solution. Do you remember this at all? Beats the heck out of the other way. And I speak from experience because I had to do them both. All right, don't worry about that, but I'm going to show you why this is so powerful. Because until you understand why it's powerful, you have no interest in learning, usually. So let me show you what I'm talking about. Very simply, if I have a circuit like this, and I'm going to say this voltage here is some V naught cosine of omega t. With me? I'm going to show you why. I really hope this isn't from this class. I had one guy, he's a real character. Just when I'm about to make the most important point, make sure he calls me. Important. Now, resistor. And now, I'm going to put an inductor. My whole goal is this. I want to find this voltage. Or better yet, forget the voltage. I want to find this current. I'm going to make it real obvious. All right? With me? So, with what you know, if you were asked to find that current, and it would be a function of time, what you would do is say, well, I'm going to say that V naught of cosine of omega t, that's the voltage source, right? So if I come here, I get an increase of that, right? Then I have a decrease of what? Well, it'd be a decrease of I of t times r. Y'all with me? Then I keep going around and I would have a decrease of what? Remember of L di dt. You all follow me, class? Then you get minus L di dt equal to 0. What do we call that? Something we don't want to do. You can pick the word for it. It's a differential equation. It's homogeneous, but it has a non-zero function or a forcing function. Remember, you have to get the particular and the complementary or the general solution. Do y'all remember doing those? It's so much fun. Now, you guys probably can knock that out in a second because you go right to, you probably take Laplace transforms and then you get S squared times L there, and you'd knock it out and you got it, right? You can do it that way if you really want to, but you're hurting yourself. Here's how we do it. And we eliminate the need to solve that. You ready? This is the reason why what I'm showing you is important. I hope I may not have time to do it all, but I'm going to show you. Now I'm going to take that same circuit, and remember what I told you. This right here is just the real part of e to the j omega t. Remember that? Times v naught. Correct, class? So now we do this. Let me get rid of this too. You may, I'm not trying to make this stuff difficult or confusing or in any way, shape, or form overlook step. Here's that circuit. Here's how we solve it now. Instead of putting this in it, and it even gets easier in a second, we replace that by plus to minus just v naught e to the j omega t. Are you with me? We're going to say, I know that has that j term in there. Don't worry, when we get done with everything, we're only going to take the real parts of both current and voltage. You with me, class? Now, that resistance goes back in there. Something I didn't say, with any linear time invariant system, how many had signals and systems in some form? MEs? Come on, guys. Sure you did, right? You had Laplace transforms, right? You were introduced to something called a linear time invariant system. If you weren't, none of your stuff would work because you can't solve nonlinear equations, at least at this, I don't think you've been taught how to solve. Anyway, now we leave that R alone, but one thing I didn't say, this source will always give rise to currents that are I naught e to the j omega t. Can you all hear me on that? Now both V naught and I naught can have a magnitude and an angle associated with them. So I'll get to that, but I want to try to keep it simple for now. You with me? Yeah, I know, but how do you know that works? Because it's a linear system. Take my word for it. It'll have the same frequency dependence as the forcing function. This is at a single frequency. You with me? Now, you come over here and you write the inductor down, and I got an inductor here, L, right? Keep watching. Some of you probably know where I'm going with this. Remember, for an inductor, voltage for an inductor is L di dt. Do you remember me telling you that? How many do? In the time domain. Go ahead. We're still in the time domain here. We're not going to be there for long. I can put down over here v naught e to the j omega t. Let's say that's right across the inductor. Follow me? Just assume that voltage is across the inductor. Well, what current would be developed? That would be L times the derivative of I, just hang with me, with respect to t. You notice that I have I naught e to the j omega t as how it varies with time, right? What is the derivative of e to the j omega t with respect to t? J omega times e to the j omega t. So it's L times j omega t times I naught e to the j omega t. This is the last point. Just go with me here and I'll let you go. I apologize for holding. So finally, at the end of the day, you can see that V naught over I naught for that inductor is just equal to j omega L because the e to the j omega t's cancel. Can everybody see that? How many can? All right, what actually happens, and I'm not going to have enough time. When you go around here, all those e to the j omega t's cancel. And I'm going to show you how we can create a source that's got a magnitude and angle, find the current in a very easy way. I didn't get where I wanted to, but I got where I needed to. I'll see you Friday. I'm going to pick up there. You will get a quiz. Don't miss. And please.